Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Study on the effect of varying temperature of viscosity modifying admixture, V.M.A, on properties of fresh self-compacting concrete job. O. Fredrick 1, Joseph Emmanuel 2, Dakas IIAUDU 3, Aaron J. Ango 1 Department of Building, University of Jos, Nigeria 2 Department of Building, Federal Polytechnic Mubi, Nigeria 3 Department of Building, University of Jos, Nigeria 4 Department of Architecture, Abu Zaria, Nigeria. Abstract concrete is one of the most widely manufactured materials in the world. Today's concrete has to fulfill a wide range of requirements in both the fresh and hardened state. In most cases the properties of fresh concrete also affect the quality of the hardened concrete and ultimately its durability. This means fresh concrete has to be correctly proportioned and must remain homogeneous during placing and after compaction in order to avoid effects such as bleeding and segregation. Self-compacting concrete is a concrete that is able to flow and consolidate under its own weight, completely fill the formwork even in the presence of dense reinforcement, whilst maintaining homogeneity and without the need for any additional compaction.Self-Compacting concrete, SCC, differs from the normal concrete as it has the basic capacity to consolidate under its own weight. But the performances of self-compacting concrete at varying temperature often encountered on sites were ignored. To minimize the effect of the temperature, no adjustments to the concrete mixes due to temperature effects were made on the workability, hence ensuring the constant temperature has become a problem at the construction site. This study investigates the effect of varying temperature of viscosity modifying admixture on the properties of fresh self-compacting concrete. It establishes the effect of Ochre mucilage on the properties of fresh self-compacting concrete. It also establishes the optimum for Ochre mucilage extract uses as admixture. The mixes of concrete are rich mixes, 1:2:3 mix ratio of grade 20 concrete respectively. The dosages of the admixtures were 0.0%, 0.3%, 0.5%, 0.7%, and 1.0% weight of mixing water in the corresponding mix, and the varying temperature of V.M.A used were 27 OC, 200 OC, 250 OC, 300 OC and 350 OC. In order to assess the performance of Ochre mucilage in this research work, the laboratory tests were conducted for up to 28 days. The results shown were for fresh self-compacting concrete at varying temperature as stated above, while for hardened self-compacting concrete were for 3 days, 7 days, 14 day, and 28 days to determine the low strength, medium strength and high strength of self-compacting concrete. The key function of a V.M.A is to modify the rheological properties of the cement paste. The objective of this study is to focus on the effect of varying temperature of viscosity modifying admixtures on the properties of fresh self-compacting concrete. For this purpose, Ochre mucilage was used as V.M.A. The experimental results have shown that Ochre mucilage is a kind of natural water-soluble polysaccharide, very effective in stabilizing the rheological properties of self-consolidating concrete. Keywords: self-compacting concrete, viscosity modifying admixtures, workability, and mechanical resistance. 1. Introduction. Self-compacting concrete was developed in Japan 1980s in order to achieve high-performance durable concrete structures, and with the advancements in concrete technology its use has become widespread all over the world. Okamura and Aoki, 2003. Self-compacting concrete, SCC, is defined as concrete that has an ability to flow under its own weight, to fill the required space or formwork completely, and to produce dense and adequately homogeneous material without the need for vibrating compaction. Martin, 2010. The advantage of SCC in its fresh and hardened states include economic efficiency, i.e. it may consume high amount of industrial byproduct, it reduces construction noise and health hazards. Bardis and Chura 2001. Compare with ordinary concrete. SCC includes large amount of binder, superplasticizer, viscosity modifying admixture, V.M.A, Netty and Audu 2004. One of the latest innovations in concrete is the development of improved viscosity modifying admixtures, V.M.A, also referred to as stabilizers, viscosity enhancing admixtures, VEA, and water retaining admixtures. Water retaining admixtures are type of V.M.A already defined in N 934-2. The key function of a V.M.A is to modify the rheological properties of the cement paste. The use of viscosity modifying admixtures, V.M.A, has proved to be very effective in stabilizing the rheological properties and consistency of self-compacting concrete. Viscosity modifying admixtures, V.M.A, are water-soluble polymers that increase the viscosity of mixing water and enhance the ability of cement paste to retain its constituents in suspension. Schmidt, 2014. Ochre mucilage was limited in use. Therefore, there is need to investigate ochre mucilage not only at room temperature but also at varying temperature. Furthermore, most previous studies only focused on compressive strength. However, in this research temperature of ochre mucilage also been studied. Self-compacted concrete, SCC, is one of the famous types of concrete, but addition of industrial waste additives to partially replace the mixing water and treating concrete at varying temperature in SCC has been proposed for the first time in this study. Performance of concrete in normal environment and elevated temperature gives a comparative analysis, Yoshioka et al. 2014. The property of concrete to sustain in varying temperature in an environment provides an opportunity to test its behavior during fire outbreak in structures. IJERT 10 is 060405 www.IJERT.org 873. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Employment of such wastes and their beneficial effects for structures are observed in this study. Although artificial neural network, AN, is famous in predicting compressive strength of self-compacting concrete, SCC, Planck and Hirsch 2014, in this study, new variables have been tested, which are basically related to change of additives, curing conditions, change of type of additive and percentage of additives. The share of self-compacting concrete in the overall concrete production is not large. One of the reasons is a significant impact the temperature has on self-compacting concrete workability. Temperature is a factor inextricable linked to the processes of mixing and casting of concrete. The final temperature of the fresh concrete is influenced by a temperature of the components, ambient temperature, and the heat generated by the mixing. Ensuring the constant temperature is very problematic at the construction site. It is possible only during production of precast concrete. Influence of temperature on the workability of ordinary concrete is well recognized. Yoshioka, 2002, increasing temperature leads to stiffening of the concrete mixtures. The loss of workability due to the increasing temperature does not disqualify concrete mix yet, and correct casting is still possible. Workability loss can be compensated by the higher or longer mechanical vibration. In the case of self-compacting concrete, compaction process is due to the concrete's own weight. Load is caused by mixture's own weight, defeating the yield value, causing the flow of the mixture. The flow rate depends on the plastic viscosity. Increasing the plastic viscosity decreases the flow rate of the mixture. Golazewski and CYGAN 2016 showed that in some cases a significant loss of SCC workability may occur. In this case, the SCC mixture should be mechanically vibrated till it reaches adequate compaction, FIG1. Ghafouri and Diawara 2016 reached similar conclusions. According to them, above a temperature of 20 degrees C slump flow is declining with increasing temperature. This trend accelerates with rising temperature. According to Schmidt, 2014, it is possible to reduce undesirable temperature influence on SCC workability. It can be done by using suitably selected superplasticizers and other chemical admixtures. By its nature, concrete is placed under different environmental conditions. Considering the volume of research done on self-compacting concrete, temperature is a factor that is linked to the processes of mixing and casting of concrete. But the performances of self-compacting concrete at varying temperature often encountered on sites were ignored. To minimize the effect of the temperature, no adjustments to the concrete mixes due to temperature effects were made on the workability, hence ensuring the constant temperature has become a problem at the construction site. Influence of temperature on the workability of ordinary concrete is well recognized. The mechanism of the effect of temperature on rheological properties of self-compacting concrete mixtures is more complex than in the case of ordinary concrete, KA 2003. It is associated with dose and kind of superplasticizer and its temperature resistance in terms of workability. It is also associated with cement type and kind of superplasticizer. In this case, the effect of varying temperature of V.M.A on the properties of fresh self-compacting concrete need to be investigated. 2.0 Literature review. The literature behind reactant that might take place and their products when cement, aggregate, and water react together with viscosity modifying admixture were explained by some researchers like Kaya and Mitchell 2008. When a fluid starts to flow under the action of a force, a shearing stress arises everywhere in that fluid that tends to oppose this motion. As one layer of the fluid moves past an adjacent layer, the fluid's molecules interact so as to transmit momentum from the faster layer to the slower layer, tending to resist the relative motion. Inc. 1995. The yield stress can be considered as the relevant parameter that determines the flow, while viscosity is the relevant parameter that determines the flow velocity. For the stability of a concrete mixture, both parameters play an important role. While a high yield stress is required to avoid segregation at rest, a high plastic viscosity is required to avoid segregation at flow. Aside from measuring the flow of concrete, rheology is concerned with the prediction of the flow from the properties of the components, i.e. cement paste, mortar, or from the mix design, i.e. W/C ratio, aggregate content, type of cement and admixture dosage. Ferraris, 1999. As opposed to a solid, for a fluid, the distinguishing feature is the ease with which the fluid may be deformed. When a shearing force is applied to a fluid, irrespective of how small it might be, the fluid starts to move and continues to move as long as this force is acting on it. Inc. 1995. Viscosity, which is defined as a measure of fluid's resistance to flow, creates a resistance to this flowing fluid under the applied force. The decrease in slump flow and increase in segregation resistance due to environmental temperature has also been observed by R. and Domini, 2004. There are two categories of fluids, namely, Newtonian and non-Newtonian. Newtonian fluids are characterized by a single coefficient of viscosity for a specific temperature. The viscosity changes with changing temperature but remains constant with changing strain rate. 3.0 Material, method, and procedure. Many different methods have been developed to characterize the properties of SCC. As no single method has been found till date that characterizes all the relevant workability aspects, the mix was tested by more than one test method for the different workability parameters. The following test methods were used to characterize the workability properties of SCC for the final acceptance of the SCC mix: proportion, slump flow test and diameter, L-box ratio test, J-ring passing ability test, and V-funnel flow time test. 3.1 Materials used. A cement. Ordinary Portland cement of available in local market was used in the investigation. The cement used was tested for various proportions as per IS 4031 1988 and found to be conforming to various specifications of IS 12269 to 1987. IJERT 10 is 060405 www.IJERT.org 874. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 B. Coarse aggregate. Aggregate is a granular material such as sand, gravel, crushed stone, iron blast fines, slag etc. used in production of concrete. Therefore, for the purpose of this study, gravel was used for the production of self-compacting concrete. See quartz. Sand. Quartz has a hardness of 7 on Mohs scale and a density of 2.65 g/cm superscript 3. Quartz is a common constituent of granite, sandstone, limestone, and many other igneous, sedimentary, and metamorphic rocks. It has a hexagonal crystal structure and is made of trigonal crystallized silica. Present investigations of the sand properties were made. Viscosity modifying agent, Ochre Muslege, a viscosity modified admixture. Ochre Muslege admixture was used to develop concrete with enhanced viscosity and controlled rheological properties. 3.2 Experimental method. A cement content of 356 kg/m3 was used for the self-compacting concrete. Water was adjusted to yield a slump of approximately 75 mm at 27 degrees Celsius. This resulted in a water-to-cement ratio of 0.45. These mix designs were held constant throughout the program. No adjustment was made for mixes cast at either higher or lower temperatures, thus, Workability changed for mixes cast at either high or low temperature. As previously pointed out, this approach was taken to isolate the effects of temperature of viscosity modifying admixture. As there is no standard procedure available for designing the mix proportions for self-compacting concrete, R. and Domini, 2004. Proportion based on the experimental trail was adopted. 3.3 Development of self-compacting concrete. Self-compacting concrete was prepared using 1:2:3 mix ratios, 0.0%, 0.4%, 0.8%, 1.2% and 1.6% of ochre muslege, V.M.A, of W/ratio at varying temperature of 270 C, 200 C, 250 C, 300 C was added to homogeneous mixture of ordinary concrete. SCC was developed. The J-ring, L-box/Coulson static segregation column, V-funnel, and slump flow tests were performed. Cubes of dimensions 150 mm by 150 mm by 150 mm were cast. All samples were allowed to cure in curing tanks filled with fresh water. The curing process was done for 7, 14, and 28 days. After curing, cube samples were tested in a compressive test machine. The strength tests were carried out carefully on best attained samples from the stock of casted samples for different percentage replacements. 3.4 Test procedure. The cleaned base plate was placed in a stable and level position. The bucket was filled with 6 liters of representative fresh SCC and the sample was allowing stand still for about 1 minute, plus or minus 10 seconds. During the 1 minute waiting period, the inner surface of the cone and the test surface of the base plate was pre-wet using the moist sponge, and the cone was placed in the center on the 200 mm circle of the base plate and the weight ring was put on the top of the cone to keep it in place. If a heavy cone is used, or the cone is kept in position by hand, no weight ring is needed. Guidelines testing SCC September 2005. The cone was filled with the sample from the bucket without any external compacting action such as rotting or vibrating. The surplus concrete above the top of the cone was struck off, and any concrete remaining on the base plate was removed. It was checked and make sure that the test surface is neither too wet nor too dry. No dry area on the base plate was allowed and any surplus of the water was removed. The moisture state of the plate has to be just wet. After a short rest, no more than 30 seconds for cleaning and checking the moist state of the test surface, the cone was lifted perpendicular to the base plate in a single movement, in such manner that the concrete is allowed to flow out freely without obstruction from the cone, and the stopwatch started, the moment the cone loses contact with the base plate. The stopwatch was stopped when the front of the concrete first touches the circle of diameter 500 mm. The stopwatch reading was recorded as the T50 value. The test was completed after the concrete flow has ceased. Note: not touches the base plate or otherwise disturb the concrete until the measurement described below was completed. The largest diameter of the flow spread, max, and the one perpendicular to it, perp, was measured, using the ruler. 3.5 Column segregation test. A sample of freshly mixed concrete is placed in a cylindrical mold, column, without tamping or vibration and allowed to stand undisturbed for a specified duration. The mold has 3 sections representing different levels of the mold. Concrete samples from the top and bottom section and washed on a number 4, 4.75 mm, sieve. The masses of saturated surface dry, SSD, coarse aggregate in the top and the bottom sections were determined. IJERT 10 is 060405 www.IJERT.org 875. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.IJERT.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 4.0 Result and Discussion Results for flowing ability, passing ability, and static segregation. Varying temperature of ochre muslege at different percentage of replacement. Table 1 Results of fresh properties of SCC, V.M.A at room temp of 27 C, ochre muslege percent 0.00.4 0.8 1.2 1.6 Test age, min. 0.05.0 10 15 20 Slump DMM 250 300 550 600 and 15 670 Flow J. Ring DJ, MM, 248 295 542 605 658, DDJ, MM258 1012 static segregation percent 14 12 864 table, 2 results of fresh properties of SCC, V.M.A. Temperature at 200 OC, Ochre mucilage test age, min, slump flow J ring static percent DMM DDJ, segregation percent 0.00.0 250 248 214 0.45.0 280 278 11 0.8 10 500 485 15 7 1.2 15 605 590 15 6 1.6 20 610 593 16 3 table, 3 results of fresh properties of SCC, V.M.A. temperature at 250 OC, Ochre mucilage percent 0.00.40 0.8 1.2 1.6 test age, min, 0.05.0 10 15 20 slump flow DMM 250 270 490 600 605 J ring DJ, MM, 248 264 475 584 587, DDJ, MM26 15 16 18 static segregation percent 14 10 742 table, 4. Results of fresh properties of SCC, V.M.A. temperature at 300 OC, Ochre mucilage percent 0.00.40 0.8 1.2 1.6 test age, min, 0.05.0 10 15 20 slump flow DMM 250 268 475 598 600 J ring DJ, MM, 248 263 465 587 583, DDJ, MM 25 10 11 17 static segregation percent 14 9 732 table, 5 results of fresh properties of SCC, V.M.A. temperature at 350 OC, Ochre mucilage percent test age, min, slump flow DMM J ring DJ, MM, DDJ, static segregation percent 0.00.0 250 248 214 0.45.0 268 264 48 0.8 10 468 468 6 1.2 15 595 585 10 3 1.6 20 598 582 16 1 IJERT 10 is 060405 www.IJERT.org 876. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Property Slump Flow J-Ring Column Segregation Table, 6 Requirements of ACI Committee 237 Requirements Tests less 550 mm, 550 to 650 mm and greater than 650 mm. The required slump flow value will vary depending on the workability needed for a certain application. The difference between J-ring flow and the slump flow must not exceed 50 mm. Static segregation must not exceed 15%. Tests method ASDMC 1611 ASDMC 1621 ASDMC 1610 4.5 Results for compressive strength at 7,14 and 28 days of curing table. 7 Results of compressive strength test for SCC made with ochre mucilage at 7 days curing varying temp. 0 C, % replacements of mixing water with ochre mucilage 0.0. 0.4 0.8 1.2 1.6 27 28.3 17.5 17.0 16.9 16.1 227.4 16.9 16.6 16.3 16.2 250 26.5 15.9 15.3 15.1 14.8 323.3 14.2 13.6 13.2 14.2 350 22.6 13.9 13.2 13.0 12.8 Table, 8 Results of compressive strength test for SCC made with ochre mucilage at 140 AYS curing varying temp, 0 C, percent replacements of mixing water with ochre mucilage 0.00.40.81.21.6 27 29.3 18.5 17.5 16.9 16.1 227.4 17.9 16.6 16.3 15.9 250 26.5 16.9 16.3 16.1 15.8 325.3 16.2 15.6 15.2 15.2 350 23.6 15.9 15.2 15.0 14.8 Table 9. Results of compressive strength test for SCC made with ochre mucilage at 28 DAYS curing varying temp, 0 C, percent replacements of mixing water with ochre mucilage 0.00.40.81.21.6 27 31.3 31.5 25.5 20.9 20.1 232.4 28.9 24.6 19.3 18.2 250 31.5 28.9 24.3 18.0 17.8 330.3 27.9 23.6 17.2 16.2 350 29.6 27.2 22.2 16.3 15.8 4.1 Fresh properties of self-compacting concrete. The fresh properties tests of SCC mixes were repeated every 5 minutes after brief remixing, from the results shown in Table 5, 2, 9, and Figs 1, 2, and 3, it can be seen that, at 1.2% of replacement of V.M.As when the test age were 5 and 15 minutes, the slump flow, J-ring, and column segregation tests varied from 580 to 610 mm, 10 to 20 mm and 13 to 15% respectively. These results show that the self-compacting concrete used was complied with the requirements of ACI Committee 237 as seen in Table 1 to 9. At 0.4% of replacement of V.M.As the slump flow and passing ability of SCC mixtures were IJERT 10 is 060405 www.IJERT.org 877. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Slightly lost. However, the slump flow and passing ability of SCC mixtures lost significantly at 0.0% of replacement of V.M.As. Except the segregation resistance of SCC increased as percent replacement increased due to increase in temperature. Figs 3. Show the flowing ability of SCC mixtures after 0 and 30 minutes from the end of mixing respectively. Figs 1. Also show the passing ability of SCC mixtures through an obstacle after subjecting V.M.As to a varying temperature at different percent of replacement of mixing water respectively. The decrease in slump flow, due to environmental temperature has also been observed by Peterson, 1998. R. and Domini 2004. Test results also showed that the environmental temperatures had a notable effect on the fresh properties of SCC. Figs 1 and 3 show that the slump flow and passing ability at 350 OC seriously lost more than that of 200 OC. The results shown in Table 5 to 9 indicated that the addition of V.M.As percent by weight of mixing water in concrete after subjecting to a varying temperature show that, from the end of mixing, brought the SCC mix back to its initial fresh properties and maintaining a further workability period of about 15 minutes. 4.2 Properties of hardened self-compacting concrete. Compressive strength, Fig. 16, shows the compressive strength for SCC at varying temperatures. At the test ages of 0 minute and 15 minutes after the end of mixing with temperature of 200 OC, slump flow is greater than 550 mm, there was no difference in the compressive strength because SCC was fully consolidate without the need for vibration. Beyond 15 minutes, the compressive strength drops significantly and at 250 OC and 300 OC the reduction in compressive strength were 16 and 34% respectively. The drop in the compressive strength of SCC is due to the fact that the mix has lost its ability to self-compact. Furthermore, at 350 OC, slump flow greater than 550 mm, the compressive strength value was about 33.6 MPa. Compressive strength data are presented in tabular format in tables 5 and 6. The 4 test conditions included concrete cast and cured at 27 degrees Celsius, concrete cast and cured at 200 degrees Celsius, concrete cast and cured at 250 degrees Celsius, concrete cast and cured at 300 degrees Celsius, and concrete cast and cured at 350 degrees Celsius. In general, the effect of low temperature casting and curing was lower at early age strength than concrete cast and cured at high temperature. Concrete cast and cured at 350 degrees Celsius had 3-day strengths of 66 to 87% of concrete cast and cured at 200 degrees Celsius. After 28 days, concrete cast at low temperature had compressive strength nearly equal to or in excess of concrete cast and cured at 300 degrees Celsius. The effect on compressive strength was relatively small. The effect of elevated temperature was the opposite of that of low temperature. Earlier age strength was higher than that of concrete cast and cured at high temperature, while later age strength was lower. After 3 days, concrete cast and cured at 27 degrees Celsius had developed 71% of its 28-day strength of concrete made with ochre mucilage. 3-day relative strength development of concrete cast and cured at high temperature was similar to 7-day relative strength development of concrete cast and cured at low temperature. In all cases, after 28 days, the absolute strength of concrete made with ochre mucilage cast and cured at higher temperature is slightly lower than concrete made with ochre mucilage cast and cured at low temperature. 4.3 Effect of ochre mucilage temperature on the flowing ability, passing ability and segregation resistance of fresh self-compacting concrete. From the results shown in tables 5 to 9, and figs 4, 5, 6 and 7, it can be seen that, when the dosage increases, the flowing ability and passing ability also increases. The tests varied from 250 to 700 mm flowing and 5 to 20 mm passing. These results show that the self-compacting concrete used was complied with the requirements of ACI Committee 237 as seen in Table 6. When the temperature increases, the slump flow and passing ability of SCC mixtures were slightly decreases. However, the passing ability of SCC mixtures increases significantly at 0.8% dosage. V.M.A's. Figs 1 and 2 shows that the slump flow and passing ability of 350 0C seriously lost more than that of 200 0C. Slump flow 800 600 400 200 027 200 250 300 350 temperature OC 0.0% OM 0.40% OM 1.2% OM 1.6% OM. Fig 1 Effect of ochre mucilage temperature on the flow ability of fresh self-compacting concrete at different percent of replacement. IJERT 10 is 0600405 www.ijert.org 878. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org. Passing Ability International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 2015 10-5-0-27 200 250 300 350 Temperature OC 0.0% ochre mucilage 0.4% ochre mucilage 0.2 ochre mucilage 0.4 1.6% ochre mucilage. Fig 2. Effect of ochre mucilage temperature on the passing ability of fresh self-compacting concrete at different percent of replacement. The segregation resistance of SCC decreased as the temperature of V.M.A's increases due to gradual stiffening process. Figs 3 show the flow ability of SCC mixtures after adding V.M.A's dosage. The result also shows that increase in V.M.A's dosage increases the segregation resistance of fresh. Test results also showed that the environmental temperatures had a notable effect on the fresh properties of SCC. The results shown in Fig 3 indicated that the addition of 0.8% by weight of mixing water in concrete brought the SC mix back to its initial fresh properties and maintaining a further workability period of about 15 minutes. Segregation resistance percent 16 14 12 10 8 6 4 20 27 200 250 300 350 Temperature OC 0.0% ochre mucilage 0.4% ochre mucilage 0.20 1.2% ochre mucilage 1.6% ochre mucilage. Fig 3 Effect of ochre mucilage temperature on the segregation resistance of fresh self-compacting concrete at different % of replacement. Table 1 to 5 shows the self-compacting properties of concrete made with ochre mucilage as V.M.A. The slump flow test measures the degree of flowability of the concrete, which has a conformity criteria of slump flow class 1, 520, 700 mm. The L-box tests the passing ability of the concrete through obstacles and also the filling ability of the concrete. It has a conformity value of 0.75 for a class 1 passing ability. The fill box test measures the filling ability of the concrete through heavily reinforced formwork. The nearer the value of the height measured after the concrete has stopped flowing at the end of the box to the top of the concrete at the tip of the funnel, the greater the ability to compact on its own. 4.9 Temperature effect on the compressive strength of hardened self-compacting concrete. Fig. 16 and 17 shows the compressive strength for SCC as a function of the elapsed dosage and varying temperatures. At the test ages of 28 DAYS there was no difference in the compressive strength between SCC and conventional concrete, because SCC mix should fully consolidate without the need for vibration. The compressive strength dropped significantly 1.2 and 1.6% replacement after subjected to high temperature. The drop in the compressive strength of SCC is due to the fact that the mix has lost its ability to self-compact. It is obvious from these results shown in Fig. 4, that the compressive strength of SCC decreased when the temperature increases. IJERT 10 is 060405 www.IJERT.org 879. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Compressive Strength KN/M3 28 Days Curing Age of SCC made with ochre mucilage 35 30 25 2015 10 50 27 200 250 300 350 Temperature 0.40% 0.80% 1.20% 1.60% Fig. 4. Relationship between compressive strength of % replacement and temperature of ochre mucilage in SCC 5.0 Conclusion and Recommendations 5.1 Conclusion In this study ochre mucilage was used as a local additive to investigate the performance of fresh and hardened self-compacting concrete made with ochre mucilage at varying temperature and at different percentage of replacements by establishing the effect of ochre mucilage on the properties of fresh and hardened self-compacting concrete, the optimum for ochre mucilage that will be used as admixture. Also to classify the category of viscosity modifying admixture that ochre mucilage belongs to, through the measure of workability for fresh concrete and compressive strength for hardened concrete in different ages. From the results obtained, the ochre mucilage is environmental friendly because it is agrobase, vegetable, admixture, unlike mineral admixtures, and is a kind of natural water-soluble polysaccharide, proven to be very effective in stabilizing the rheological properties of self-consolidating concrete at 1.2% of replacement. As concrete mix with ochre mucilage temperature increased from 200 degrees C to 250 degrees Celsius, slump decreased approximately 20 mm. Lower temperatures increase set time, higher temperature decrease set time. This shows increasing temperature leads to stiffening of the concrete mixtures. For self-compacting concretes made with ochre mucilage at 200 degrees Celsius, 7-day compressive strength was approximately 75% of 28 DAY compressive strength of conventional concrete. At 28-day compressive strength of concrete cast at low temperature, 27 degrees Celsius, was nearly equal to that of concrete cast at high temperature, 300 degrees Celsius. High temperature of ochre mucilage at early age strength is more effective than that of later age strength. 5.2 Recommendations. This study provides knowledge and records about locally sourced admixture that can be useful in the development and innovation of new technologies in the field of construction. This will provide necessary information for the students in their future research on admixtures. It is an opportunity for the government agencies to utilize a different source of admixtures in their infrastructures, mainly buildings, highways, and bridges, which will derive cost savings since it is locally sourced. Also will encourage cultivation of ochre plant not only as food but as admixtures. References 1A SDMC 1621, Standard Test Method for Passing Ability of Self-Consolidating Concrete by J. Ring Annual Book of ASTM Standard, 2005, pages 1 to 5. 2A SDMC 1610, Standard test method for segregation resistance of self-consolidating concrete using column technique. Annual Book of ASTM Standard, 2005, pages 1-4. 3 Bartas P.J.M., and C. Chura, 2001. Improvement of working environment in concrete construction by the use of self-compacting concrete, 2, 3, 127-135. https://doi.org/10.1680/sco.2001.2.3.127 Ferraris, cf. 1999. Measurement of the rheological properties of high-performance concrete, State-of-the-Art Report, 104, 5. 5J. Simi and Martin, 2010. The Economic Resilience of Regions, Towards an Evolutionary Approach, Cambridge Journal of Regions, Economy and Society 3, 1, 27-43, 2010. 6J. Planck, C. Hirsch, Impact of Zeta Potential of Early Cement Hydration Phases on Superplasticizer Adsorption Cement and Concrete Research, 37. 537-542, 2007, 7 KAKH and Mitchell D., 2008, Self-Consolidating Concrete for Precast, Pre-Stressed Concrete Bridge Elements Final Report for NCHRP Project 18-12, 170p. 8 N. Ghaffari, H. Diawara, Influence of Temperature on Fresh Performance of Self-Consolidating Concrete Construction and Building Materials 24, 2010, 946-955. IJERT 10 is 060405 www.IJERT.org 880. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 9 Okamura, H., and Aoki Masahiro. 2003, Self-Compacting Concrete. Journal of Advanced Concrete Technology, 1, 1, 515. https://doi.org/10.3151/jack.1.510 Aoki, Nakamura, Osterson, Hallberg, and Lewin. 2003, Applications of Self-Compacting Concrete in Japan, Europe, and the United States. 11. Schmidt, W., 2014. SCC, A Solution to the Challenges of Concrete Construction in Africa. Concrete Trends African Focus, p4. 12 U.S. Inc. 1995, An Introductory Guide to Rheology. Retrieved from www.sunchemical.com 13 Zaka, P.W., Job, O.F., and Enigbago, N. 2015, Ecological Self-Compacting Concrete Using Gum Arabic as a Plasticizer. In West Africa Built Environment Research, Weber, P10. IJERT 10 is 060405 www.ijert.org 881. This work is licensed under a Creative Commons Attribution 4.0 International License.